Yeah, we were also talking about homework, right? So yeah, Tuesday. Yeah. So because I have to cover the force equation and then I'll do an example.
I have a question about this actually real quick. On equation 3, you have the closed circle integral with the volume element at the bottom. Why is it not like a surface element?
It is a surface. Yeah, this is my own notation. So I should stop using it. It's a little confusing.
Oh,
So,
yeah.
So I think what I mean is here. So if you have a volume, right, and then that has a surface, right? So when I say a closed integral, it is not very clear closed integral, which closed integral. So I should say closed integral on this S, or I can say the surface that encloses the volume.
I see.
So for a given volume, there is a surface. Instead of creating a new notation, as I say, this is the closed integral enclosing the volume. But when you say V, oh, that's a volume. So what? That's a surface integral. So that's a confusion. I suppose. I think it's not standard notation, so I should stop using that. But that's what I meant. Yeah. Okay. This is suppose. Okay. Set up. So we said that we have homework. So homework 2, you. And okay, for it. You have an exam on February 15. One is on February 15, which is Tuesday. Yeah, we are discussing what I have been calling conservation principles, and we will use this to calculate the stress on a medium. That's a nice interpretation of this whole Maxwell's equations. But let's see. So we have been deriving conservation principle. There's a lot of conservation principles in electromagnetism. We will stick to 3 of them: charge conservation, energy, and momentum. There are more relations one can derive. Angular momentum is clearly one of them. Oh, thank you. So let me write down the Maxwell's equation. So we have rho and P is equal to 0. Here the definition is that D is equal to epsilon naught times E, and D is equal to mu naught times H. if the materials involved, this has to be written in the frequency space, and there are details in there, but the expectation is that we have covered those things in the earlier semester, and now we are interested in the time dependence. So this is del cross E equal to minus time derivative with respect to T, and del cross H is equal to time derivative of T plus J, the current. That's your Maxwell's equation, and just based on this, one can manipulate these equations and conclude a few more equations. And first one he said is conservation of charge. And that's d rho by dt plus is equal to 0. Actually, let me write this as plus 0 is equal to 0. So notice this means that there is no source. This 0 has this interpretation that charge cannot be created or destroyed at a local.
Yeah, in the last class you discovered about the fluid.
Exactly, right. So, as you're saying, if you were to integrate this, this is charge in a small volume is equal to how much charges are coming through the boundary plus whether they are created or not, created or destroyed. That's a flux interpretation. And the second we derived is conservation of energy. This plays an important role in optics. It's called, I think it's a source of optical theorem, if you have one, but in general. So you say time derivative of energy density, U is electromagnetic energy density. Notice the connection here, time derivative of something, right? Time derivative of charge density, here it is energy density, plus a divergence of some quantity. Here, this will be divergence of S. So J here is interpreted as flux of charge, right? Charge density, if you want, flux of charge. S will be flux of energy. Right? How much energy is going across from the boundary? Here, we said charges cannot be created or destroyed, but energy can be created or destroyed. What do you mean by energy? Can be electromagnetic energy, can be used up by a charge to move, right? So you've destroyed electromagnetic energy and converted into kinetic energy. So in that sense, it can be converted, and that shows up as J dotted with E. That's the only way electromagnetic energy gets converted, so that electric field leads to a current of the like movement of charges. So that's equal to 0. This requires a definition of U and S. So all the students are in the class, it's hard to concentrate. I used to be decent when I was teaching online. Okay. Okay. So what is U? U is electromagnetic energy stored in space, right? It is not in any matter at every point in space. There is a say energy per unit volume, and this is written as D dotted with E, which is familiar, right? Half epsilon naught E squared. Right? That's the amount of energy that's stored inside a capacitor, for example. But you can save something in magnetic field also, and it is B dotted with H. again, I think it's good to write it in the familiar form, epsilon naught E square plus of P square over mu naught, right? That's how you see it in elementary physics. Oh, again, so that's your energy density. How at each point energy density changes is given by how much it goes across through the boundary plus whether it's created or not. This is called the flux of energy. Current density is the flux of charge density. This S is the flux of energy density, and it has a special name. It's a pointing vector. That's a standard thing. So this is E crossed with H. This is flux of U, if you want, or it is the pointing vector. So that's what we did. And this, we will use this equation. This plays an important role when you're doing radiation. You will have a small region where these charges are moving around, and we would like to know how much energy comes out in a detector, which is really far away. So you will put a big sphere and calculate how much energy, the flux of energy, how much energy is crossing a surface. And that's when you will use this. For now, let us proceed. And if there is a conservation of energy, let's see conservation of momentum, right? And there will be a conservation of angular momentum. And there are many conservations you can think, but standard ones are charge, energy, and momentum. So to that end, let's begin fresh. So for this, we had started with a power equation. Let's start with a force on a charge, Lorentz force, F is equal to Q times the electric field plus Q times V crossed with V. That's a force on a charge, but we would like to think in terms of charge density. So immediately divided by volume. Charge per unit volume is charge density. We will say this is force density now. The understanding is that there is some distribution of charges in a region, and this is the force per unit volume. So that's equal to charge density times the electric field plus current density times the magnetic field. So that's our equation. Let's begin with this equation and see if we can interpret it as a conservation equation. So let's replace all the rows and J's here. So I'll stop writing the R and T dependence. It's understood that there is an R and T dependence in there. So F is equal to charge density is using Maxwell's equation. Now, what is the P times E. That's a scalar multiplied by a vector plus the current density. Let's use the fourth equation. So I have del cross with H minus dt. Okay. So I started with the force equation, wrote it as a density equation, and replaced all the sources, right? I want completely in terms of the fields. Then let's play the same trick we did when we were doing this. If del dot D is equal to rho, I can write a corresponding equation for del dot B because it says 0. So let me write del dot B here. I can add, right? I can add or subtract. I'll decide on that in a minute. Del dot B is 0 anyway. I can multiply it with, here it was multiplied with E, so I'll multiply it with H. That's 0 anyway. Do the same thing here. This is equal to 0. So I can add or subtract del cross E plus dB by dt. That's 0. That's this equation. That is 0, the third equation. And I can multiply with anything. I'll multiply with D. Okay. Okay. Any questions?
The last one, which equation?
I use this equation. This is 0. Like if I put this onto the left, that's 0, right? So del cross E plus dB by dt is equal to 0. Right? And now I have to decide whether I want to do plus or minus. So looking at this, I want a minus here. So this I will choose minus. And I don't know what to use the other one. E, H, and B. Yeah. So for now, let me say this is plus. But I might come back and change that, right? It's a 0 anyway, it doesn't matter whether I do a plus or not. The basic idea is that I want to write this as a derivative at time of something and divergence of something else. And then I can interpret it as a flux equation and then. Okay, so it's clear this term here, the time derivative, two time derivatives combine. Actually, they don't combine. So I changed my mind. This is plus and this is minus. Because they don't combine, right? This is B cross B and B cross D. So they don't combine. So I changed my mind. So this is plus and that's minus. So that's equal to, let me start with the time derivative term. So this is D cross B. So let me write this as D by dt crossed with B. The time acts only on D. And let me write this, the second term here, the cross product reversed. So this will be minus of D crossed with dB by dt. Hopefully that's clear, right? I took care of this term and this term. The two time derivative terms. The time derivative terms, I wrote it, I flipped the cross product, which gave me a sign of negative, an extra negative sign. Is that clear? Okay, and then I have a few more things here, so let me collect them. So that's plus del with D, E, and this is plus del cross with H, crossed with B. Oh, sorry, I don't want to write it like that. I actually want to write all the E's on one end. So I'll combine this with this. Cross with D. So now I have taken care of this and this. And the other two, I'll put it separately. So it's minus L dot with B. Actually, again, changed my mind. There was this choice I had, right? That this could have been a plus or a minus. I choose this to be plus. Okay? So that this is plus. And then there is a symmetry, right? D, E, B, H, E, B, H, B. Right? So if I do this for one, then I can, the other one is identical. I just have to replace that. So they should look very symmetric. They will come out as this. And this is clear what it is. This is nothing but time derivative of or minus time derivative of D crossed with B. So this is D crossed with D. Once it will hit D, that's this. It will can hit B. That's the second. Okay. So let's try to process this. The idea is I have a time derivative. I have a force which will be interpreted as the source term. So this, the idea is, can this be written as a total divergence? So if I can write this as a total divergence, if I can write one of them as total divergence, that's good. Enough, the other one is also good. So let's investigate that. Any questions at this stage? Okay, so yeah, let's start with del cross of cross. So this is E cross with B. Let's begin with that. So that's this term. If I can process that, and do something. So this is to begin with. This is nothing but D crossed with minus D crossed with del crossed with D. So that's double cross product. That's equal to this hits only on A, so this is back cab, right? So this is D. Remember your A crossed with B crossed with C. It's back cab, right? So first there is B, and then A and C come as dot product, right? Minus of A dotted with B times C. This is typically written as B A dotted with C. Right? So that's here vector product. But I don't want to move this to that side because B is a derivative. Right? Since B is a derivative, in this way of writing it is not very clear how it will act only on C. Right? So let me write this as D, and then gradient acts. So this is a free vector now, and the gradient acts on E, and this is dot product. Is that clear? No. Or if that's not clear, so maybe if that helps, This is gradient of E, but this is a tensor dotted with D. Is that clear? So that's this side. But now B is acting only on A. Minus of D or plus of D dotted with gradient E. Any questions on that? Like we manipulated with equations, vector equations, but hopefully. Any concerns, questions? Okay. So let's again, I want a total divergence, right? So let's see if I can write this acting on D itself. So let's say I'm now going to manipulate again. So let's say this is supposed to act only on E, but I'm going to make it act on both. That's a mistake, right? That's not correct. Right? That's not correct. But then I just have to subtract out this. Right? So I just have to subtract whenever it acts on that. So I rewrite this. So this is, I have to subtract means it is addition. So it is plus of del of D dotted with E. This plus this is this. And of course, I have to leave this alone. See. Is that clear? This is what I wanted to do. Thanks. Huh? Did something cancel?
Second two part, can I turn it formula?
This two you mean? I'm because we have to add this also, right? So this is also in here. So that's the point. But del dotted, so I don't see that term yet. Give me a second. Yeah, this is the term that is bothering me. Let me work. do this in a slightly different way. Okay, maybe make it easier. Okay. Make it simpler. D is epsilon naught E, right? So this is equal to minus epsilon naught times E plus epsilon naught times E. There's nothing wrong with that. Right? So it's the same thing, I wrote it. But now there is everything in terms of E, right? So moving around is easier. And, yeah. And first observation is that gradient of E square is equal to, I can have 2 times gradient of E, right, dotted with E. That's, if I were to do this, it is 2 times E dotted with E. I can take the gradient of one of the E's, that's this, or I can hit the other E, but that's going to be the same thing. Right, so because I can write that as a factor of 2. And that I can use here. So that's one thing I want to do, but now we want to do the same thing here also, right? So what is E? So let's see, gradient dotted with E times E. So again, this is now both in here. So I have to decide whether I'm hitting this or this. So when I hit this, this is still dotted with E. Times the second vector. That's the dot product. But I can also hit this. When I'm hitting this, I have to flip. Right? So it is plus E dotted with. Is that clear? Once I have that, we can go back and think in terms of E and D. So this is the same as if I were to put in an epsilon naught, that becomes an E dotted with D. Right? So put in an epsilon naught everywhere. Let's say epsilon naught here, and put in an epsilon naught here also. Epsilon naught. Epsilon naught. So the two equations then tell me that divergence of D dotted with E. This is this equation being rewritten. It's equal to 2 times L dotted with D. And E. Oh, sorry, that's not what I meant. So this is the tensor right, gradient acting on the displacement vector times E. Right, that's this equation. Is it clear how the manipulation is working? Yeah. And here, this is divergence of E. E is equal divergence of D alone. D plus D is basically algebraic manipulations. This is the situation. And now I want to use this up there. So now that I've written it in this form, I can get rid of this. So what is this now? I have del E dotted with D. That is that showing del E dotted with D.
That's del D dot E.
Oh, which one?
Nebula.
Oh, this one?
No, up one.
Here?
Yes. Otherwise,
Oh, is this a mistake here? Hold on. What did it say? So gradient
DAC.
acting on E dotted with D, right? That's okay, right? So for example, D cross, what I was doing is D, A cross B cross C, right? Right. So this is the free vector, first back cap, right? So this is the free. And then I have to dot these two, right? So this is D and E, right? I have to dot this. But the only way I can, so first I have to act on this also. So I bring this on the other side to dot it. Right? So that's what I did there, right? So that was the idea. But probably what you're trying to tell is that, oh, that's the, maybe I won't see it in this form, but then there was an epsilon naught, I could have put it here or there, right? Right, or here or there. Right. So maybe this one can, it is better to write this as E times B. Right. So that it doesn't matter, epsilon naught is free to move around in that way. So if I see that, I can replace this here. So this is equal to minus half of total gradient of D dotted with D. Right, that's the first piece. And the second one is D, that's this term. Again, I subtract out, so this is equal to this plus of DE and I have to subtract this out, so that's minus It would have been nicer if I had gone a few steps and got it exactly, but I was not able to see these things clearly in my head. Write it down. Clear? Any questions? Okay, if that's the case, I can bring this to the left. And that should be what we have earlier, right? This is the divergence of D times E plus L cross E cross D is equal to, this is a divergence of so this is let me start from here. Oh, I've taken this out, so this is dotted with E. And that is this term, which is going to be written as divergence minus of divergence of They're very clear. Sorry, so too many steps I have to go around about, but hopefully it helps. Our goal was to write it as a total divergence, right? But this is not really a total divergence. This is a divergence and this is a gradient. Right? So it doesn't seem to have played the role, but notice that if I have a divergence of a scalar, so notice this is a tensor right here, right? So this is a vector that comes out. So if I have a gradient of a scalar, I can interpret it as, so this is a vector now, this is what I'm going to do. This is the same as 1, right? I can always multiply by a 1. And then there is an f. Is that clear? Because a vector gradient of 1 is gradient itself. Right? In index notation, this means del I, and then del ij is del j. So this is a way of changing the indices from 1 to 2, right? That's just a trick we are going to use. If I use that trick, then I can see that this is a total divergence. So it's the tensor, so this is minus of 1. So in fact, let me take out a negative sign here and write this a little bit. If you've already copied it, otherwise I'm sorry to erase that. The minus. Let us write this one ahead. It's 1. A good bit of manipulation. And that's this, right? That's this term here, the second term that appeared here. If I were to replace this quantities, I can immediately conclude, because this was just a vector identity in a sense. So this is also true. That I replace all the d's with b's and e's with h. I can immediately conclude that this also must be true. That's equal. Pretty much identical. questions? Okay, so if that's the case, then I can go back there. Change the- Go back and go to that equation. So my equation becomes f. The first term was just minus time derivative of b cross b. Right. And the second one is these two, right? So I'm going to write this all together in one piece. So it's minus of put this together here. Okay, let's see. Started it. I'm going to write all these terms together, right? These two are, this is all together. So I have a 1, which is coming as half d dotted with d plus half of half d dotted with d and d dotted with h. And then there is minus of e without any operations in between, minus EH. Move this all to the left, and I'm going to write this as time derivative of whatever is there in the time derivative. I'm going to call that G. It's G definition, G. And whatever is there here, right, this is a tensor. That double here, this is also a tensor. I'm going to write that as T. So this is plus. So I'm going to move it to the left and say this is a tensor. So this will be written as T. Okay. And there is this force F, which force density F. In this way, we have succeeded in writing this as a flux equation, right? But this time it's a vector flux equation. Like the vector earlier, we had a scalar, vector, and a scalar. Now this is a vector, so these are 3 components that satisfy this flux density. So let's write what is G. Define these things. G was equal to D crossed with B. Right. And T now is 1 unit diatic multiplied by whatever this is energy density. Right? That was just U, energy density, minus of the tensor associated with energy density. So this is E H.
Energy density or
Oh,
the
T?
flux? Yeah.
Oh, this will be the flux of G, right? So I'm going to bring that in a minute. So now we have to interpret this, give an interpretation to this. This is force per unit volume, right? And this is time derivative of something. Time derivative of what is a force? Momentum, correct? Time derivative of a momentum is a force. That means if this is force density, this can be interpreted as a momentum density. So this will be interpreted as electromagnetic momentum density. Which is a vector G. It's also interesting to see that this is equal to, this is also equal to, at least in free space, this is epsilon naught, mu naught times the Poynting vector, right? Which means to say that if there is energy moving in one direction, it also carries a momentum with it. I think of an ocean wave. If energy is moving, that means it's carrying some momentum with it, right? So the flux of energy is connected to momentum. And now we need an interpretation for this. Clearly, this is the flux of momentum, like how much momentum is going out of a region. So this is the flux of momentum density. In our terminology, right? In the fluid dynamics terminology, that's how you would. But this has a special name associated with it. This is also called energy momentum what's this? I think this is flux tensor. Energy flux tensor. You can say electromagnetic flux tensor. And you can see one interesting, any questions at this stage? Yes.
In the book, the momentum density is written with a 1/4 pi c constant. I was just curious.
Oh, that's because the whole book of Schringer and Milton, they work in Gaussian units.
Okay. Oh, right.
Right, and Gaussian units works with this 4 pi rationalization is coming into picture. Okay, so that is a challenge you will have to work with when you go. I think I decided sometime early on that SI suits better in a classroom. If you're doing theoretical physics, most of theoretical physics is done in Gaussian units when it comes to electro, or in general, it's done in Gaussian units, just so that you don't have to carry on the c speed of light. You just don't solve epsilon naught, mu naught here, right? So this keeps lingering on. There's nothing wrong in it. Dimensionally it helps a lot often, but people don't like it. So in Gaussian units, this is 1. Speed of light is 1. So it comes at a price that dimensional checks are not possible, or that intuitive dimension checks that we do at an undergraduate level doesn't work, but it gives some cleanliness, less variables in an equation. So it's strongly preferred, like among theoretical students, to use this. They call it natural unit. But in a classroom setup where it's not just theoretical physics, there is everyone sitting in, and they often students like to connect with experiments. It is good to have SI units right in front of them. So I somewhere chose to do SI units. That's the difference that I'll see. Okay. So as one thing, a nice feature in that one should highlight here, and that is that this is speed of light, right? So this is 1 over c squared if you want. So s is equal to c squared times g if you want. And this is energy per unit. So U is, remember, du by dt plus del dotted with S plus J dotted with E is equal to 0, right? So that's the energy conservation equation. Think of the units. This is energy per unit volume. This is the flux of energy per unit volume, right? So what is the dimension of S here, per unit volume, if you were to get rid of? So dimension of S is, this is a length over time. So this is speed, the dimension of speed times dimension of energy, right? Dimension of energy density, if you want. And G similarly is momentum, right? It's momentum per unit volume. So we have speed of light, c, dimensionally speaking, speed of light times dimension of energy density, energy per unit volume, is equal to speed of light squared, dimension of speed of light squared, times, this is momentum, right? So this is g per momentum per unit volume. Very broadly speaking, this is c cancels out, and per unit volume. So what you're saying is that energy, there is an energy here, which is speed of light c times momentum. Like something moving with speed of light has an energy that this is the first time that, if you want, like remember that Maxwell's equation came in 1860, 65, right? 62. It was written down in 62 by Maxwell. And Einstein gave his relativity theory in 1905, right? But right here, you could have seen that this was realized. I mean, I think Heaviside and other in 1880s, they did see this. So this is a signature of relativity right away showing in there that, okay, there is something moving in speed of light. What is the energy and momentum associated with that? So these are signatures of that. But of course, it required Einstein to give this interpretation of relativity, which is much more fundamental than the way we are seeing here. Okay, so that's so this is going to be our equation. This is conservation of momentum. And we said that this seems to be, we called this stress tensor, even though this is flux of momentum. So notice that if you have an ocean wave and it is moving, think of an ocean wave which is moving. If you have if you're standing in that ocean, you feel a pressure, right? You will, you can even get pushed off or by an ocean. The same thing, if you're having an electromagnetic wave, the question is, can it push something, right? There is light coming in, this light here. Can it push something? And have you guys seen this toy where if you keep it in the sun, it rotates? Familiar? Like light can actually move things. Can it move things? If I put if you're in space, I shine a laser at you, will you move?
Will I move?
Yeah.
I mean, if it penetrates through my body, I think it will affect my body. But moving my whole body, I think it will a strong electromagnetic force to move the whole human body.
Strong laser.
Yes, strong laser. But
Yeah, that's what
or not even strong laser. If you're in space, every tiny bit of energy you have to make, right? So it has to go somewhere. So you start slowly, and then it might be a very small speed, but you will move, right, in space because there's nothing to stop you there. Here it may not move you because you're standing on the surface. There is not much that can stop you.
I mean, it's not that obvious, I mean.
Yeah, it's not obvious, right? And the basic idea, then the question comes, okay, how strong do you need? So here's so that's a quiz component to this course, right? So let's have the following. Okay, so I should have brought that with me. It's in my office. If you guys next time come to my office, on my window, there is this tiny glass thing. If you come in the early morning, that really moves. That really moves fast. But let's see what that is. That's what I want to highlight at this point. Okay. So this, as I said, Maxwell gave these equations in 1860s, and around 1870s or 80s, this was felt that all this should be there. Heaviside gave these equations, and somewhere around 1890 or probably even 1900, Crookes, right? This is the name of a person. This is Crookes. This is called Crookes radiometer, I think. So what he did is that he created a glass tube, and glass tubes are really easy to, you see glass blowing. Have you guys observed glass blowing? There are good videos on that. In SIU, there is a glass blowing department. I'll encourage you guys to go, and maybe you can even join them as a club and learn these things. It's a pretty nice art, and relatively, it's a skill, of course. Even now you blow and do that. So it's kind of a nice thing to do, to explore what is going on there. So basically you have a sphere. So this is a glass bottle, let's say, and you can suck out all the gas from it. So you can create a vacuum chamber. And that's relatively easy to do, like sucking things. And they learned these techniques very quickly. And in this, the idea was you just keep a fan, you build a small, another metallic object or not, doesn't have to be metallic. And this is a fan-like structure. So this is one piece there, two pieces, there's a third one, right? So if I were to see this from the top, this is basically, this is a 3-piece, it can have a 4-piece there. That's a blade, like it's like exactly like a fan. And these are surfaces, right? Is that clear? And since I have taken out all the gas from here, this is pretty much a vacuum, and it is reasonably easy to rotate here. This is just as a cap, you just follow on it. So if the friction is reasonably low there, it can actually move. Right? If you push on it, it can move. So it is free to move around in here and here if it can move in this tube. Yeah. Now the idea is that if let's say color this as white and this is black. So this is black. And this is white, right? So this. So this is black, that's white. And light, when it comes on a black or a white surface, there are two things it does, right? So for example, if it's on a black surface, light comes in and gets absorbed into this.
Black body.
Yeah, think of it as black body radiation, like basically it absorbs everything. That's one thing. And we are taking an ideal situation. It typically doesn't happen, but let's say it absorbs all of it. If it's a white surface, what is happening is that light comes in and goes back. That's a white surface. It is like saying you throw a ball on a sheet on a wall there. It can either get stuck there or it can bounce back. And the question is, which one will it move faster? So if I were to throw a ball at you, so there are two possibilities. You can push it backwards, like you can have an elastic collision where it moves back with velocity v, or you can catch the ball. Right? Which one will give you more? Either way, you will move, right? Because someone has hit it. Let's say you're on a frictionless surface, you will move. Which one will have more velocity? Catching it. So let's see. So let's say both were moving with velocity v. So this is a ball, right? So mass times velocity. This is mass times velocity, right? Here at the end, momentum has to be conserved. This has to. So this is your P initial. So P final, this surface, because there is nothing else, right? So this has to move with P initial, right? Here, this is P initial and it goes back with a final, right? So this is P initial. It goes back with P initial. So the question is, what is this P equal to? So P initial to begin with has to be conserved. So this is minus P initial. Right? So plus P. So this one is 2 times P initial. And that's your final velocity with which you move. So that's your P. Right? So it is 2 times P initial. So this is where you catch, and this is where you reflect off. Right? So the final velocity of this is 2 times, if it's the same mass, it will be 2 times that. So catching is sort of less. Is that clear? So that's not very important in this analysis. Main thing is that, okay, you can, on one side, it is having less momentum than the other side, if it is uniformly brittle. But you can always do this problem as, okay, you have having radiation only on one hand. So there is light coming in here from one side and light coming in here also. There is a momentum transport here, there is a momentum transport here. This is more momentum, right? So this will move this way. Is that clear? Even if I were to shine the torch from here, it will be the same analysis. So white or the black should lead if you want. Correct. So is that clear, the analysis that I'm talking about? Okay. So that's what Crooks tried to make. And he made this and it really moves. And it's in my office. I can assure you, it really, I mean, it's early morning, the sun is bright on my window. And it really moves fast, maybe about 5 or 10 revolutions or rotations per second. Right? So you can see this going pretty quick. But then it was realized that actually that's not what is happening. Right? If you really calculate how much energy light has and if it is moving, so light really cannot move this. That's as you said, right? It's really heavy. Like you're very heavy. Is light going to really move me? Right? And there were questions raised, and then the following argument was said. It was realized that it is actually not going this way; it's going the other way. And using this argument, black should lead and white should trail. Right? When you closely see that, it is actually going the opposite way. Again, you can see this in my office. It is actually the opposite way that is happening. And then you say, "Oh, what is happening here?" And it turns out, at least this is the argument I never completely understood this. This is that now it is not the light that is actually, or light is playing a role, but it is not really what we are talking about as the momentum of light coming in. This is not perfectly vacuum. It is actually, or it was noticed that Crookes did not actually create a perfect vacuum. In fact, if you make a perfect vacuum, it doesn't work.
It doesn't work at all.
It doesn't work, or it doesn't rotate. At least with this much of friction, it doesn't rotate. So using normal visible light from sunlight, it doesn't. Then it needs more force. But then what is rotating it? But if you fill in a gas, it does work. And then it was realized that black has a temperature effect also, right? So this is hotter. Black absorbs more light, so it is hotter, and this is slightly colder. And that leads to thermodynamic effect. Temperature gradient. This is hotter to colder, and gas tries to move that way, right? And this rotation comes in. So Crookes radiometer, even though it was made to show that light has actually momentum, was not really the correct description. It is some other phenomena that is happening. So your quiz is to describe this. However, I almost described it, or if possible, now I'll try to bring that tomorrow, and I'll show that. What I used to do is, it's not here. We sometimes teach in this conference room, right? There was this. If I had a dryer, I can actually use heat to make it run. Put it in the dark and actually forget the light and just use a hair dryer, and just using heat, you can actually make it move. But light is not the important factor, the heat that's doing that. But in principle, you can actually make things move in principle, but maybe you need a lot more energy, or it should be a lot more small. Don't make a human move as you were suggesting. Instead, make a small graphene sheet move, for example. Graphene is really thin, and if you ever strike light on it, it will actually move. And what we will do on Thursday is we'll actually calculate this stress. So this is a pressure now, right? You're having a pressure and a force per unit area. We'll calculate this pressure force per unit area on a surface. And those interpretations are kind of nice. Yeah, I'll stop at this stage. Thank you.